ship-based oceanographic transects. All right. So these are, I'm calling them repeat oceanographic transects, or we call them hydrographic sections. They come from the World Ocean Circulation Experiment in the 1990s, the CLIBAR CO2 program in the 2000s, and now from GOSHIP, the Global Ocean Ship-Based Hydrographic Investigations Program, in the 2010s. And so this is some work that Sarah Berkey did. It's actually an update of it in 2000. She first did it in 2010 when she was a PhD student working with me. And we decided to use all these repeat hydrographic sections and just look at the temperature trends along the section. So they're sampled like once a decade, which isn't very often, right? But we did see some consistent patterns. We see forming in the below 4,000 meters, and that you see in this plot. It's strongest around Antarctica. It grows a little weaker as you go into the South Pacific. The North Pacific, you can't really see it on the projector. But that is a very light shade of yellow. It's actually all warming up there, just very slowly. It's warming in the Eastern Indian Ocean and the Western Atlantic. The stippled regions are where we don't have enough data to predict a trend with any confidence. We can't distinguish the trend significantly from zero. Right? So there's a lot of places like that with these repeat hydrographic sections. So this, as I'll talk about a little later. So this is sort of a decadal trend. It arises from a major reduction in the formation of Antarctic bottom water, the coldest, densest waters in the planet. That happens around Antarctica. I'll talk about a little bit more about why that is near the end of the talk. But the uncertainties are about 50% of the signal. So this is about 8% of the global energy imbalance, but it could be 4%, could be 12%, right? It's not. It's actually fairly uncertain. And it's also always about a decade out of date because these are based on repeat hydrographic sections. This is a big international effort, but people only get to these sections once every 10 years. So even if you update it every year, you know, it's 10 years out of date, basically. So we're not really monitoring this interesting and changing and important situation in real time. Oops. Let's see. So this is just one transect, and this is actually we looked at this in. I first looked at this in about 2005, I think, just after the second transect was completed, and this really started me on my journey of looking at deep and abyssal warming. I have a confession to make. Back in like 1999, some colleagues published a study in journal Science that showed this very small warming was about 5 milledegrees over a couple decades. And I got called by Richard Harris at NPR, the science reporter at the time, and he said, "Do you think this is significant?" I was like, "I don't know. It's pretty small. You know, the measurement error is about 2 milledegrees, so this is 5 milledegrees. It's just over the measurement error. I don't know. I haven't seen it, but this section made me a believer. After that, so we looked at this, and this is a section of mean temperatures, are the black lines. The trends are in colors. The scale is off to the right. Again, it's sort of plus or minus 8 milledegrees C a year. But what you can see here, and this goes from the Scotia Sea at 60 south to the equator at 60 north. It goes from the surface down to 6,000 meters, close to the bottom of the ocean. So this crosses the Scotia Sea, the Argentine Basin, and the Brazil Basin. And so there's a few things that we've got to use. These are contoured thick lines at 1 degree C intervals. This thick line down at the bottom that's sort of at 3,000 meters in the Argentine Basin, and then deepens down to 4,000 meters and then stays here is the, I think that's the 0 degree C contour. This is the 1 degree C contour and the 2 degrees. You can see this large gradient between 1 and 2 degrees. It's down at about 4,000 meters. That's actually a contrast between the cold Antarctic bottom water, which is formed in the south and going north in the west in the Brazil Basin, and the warmer North Atlantic deep water, which is formed up in the north and going south. So these things are sort of moving in opposite directions. There's a big, strong thermocline between them. But you can see everywhere below that strong thermocline is warming, right? You see this really strong warming signal down in the Brazil Basin. It's a couple milledegrees C per year on average. Same in the Argentine Basin and in the Scotia Sea. You also see warming actually at mid-depth in the Southern Ocean in this section. And so this is from 3 occupations. They were done in 1989, 2005, and 2014. So we went back and revisited it in 2014. But the Argentine Basin, say, warming rate is 1.9 plus or minus 2.2, right? There are these eddies. These are basically the vertical stripes in the temperature are basically mesoscale eddies. Those have a scale of about 170 kilometers on average in the ocean, and they're the primary noise source for the uncertainty. And so this short section of the Argentine Basin actually doesn't give us a statistically significant warming assessment. The Brazil Basin were a little better. If you go back and look at that map that I showed previously, you can see that's the section we were just looking at. The Argentine Basin is simple. The Brazil Basin is actually statistically significant. All right. But we're going to go on and try to quantify these using a deep solo float data as well as the hydrographic data and see if we can do a little better than plus or minus 50%. So this is in terms of trends. This is a deep solo float. This was developed by the Instrument Development Group at Scripps. The PMEL units that we deploy are built by MRV Systems. Scripps built and deploys their own. They are capable of 200 plus full depth CTD profiles over 5+ year lifetime. In fact, the first one that Elizabeth deployed back in 2018 has now done 250 deep profiles, and it's still going strong. So these are robust and actually capable instruments. They are, the primary pressure case is a 13-inch diameter set of mated glass hemispheres. So that's amazing. That's something to cycle, down to 6,000 meters depth, which is basically 600 atmospheres of pressure, right, and back. But the glass is pretty strong. That spherical straight shape, of course, is the best for compression. And it's actually closer to the compressibility of seawater than the aluminum cylinders. And that makes them more efficient to run up and down because you don't have to change the volume as much. So they have an internal oil bladder here. They have an external oil reservoir here, a high pressure pump, batteries to power it, as well as the electronics and the telecommunications. A CTD that measures temperature, salinity, and actually temperature, conductivity, and pressure for once you get salinity, density, and depth, all kinds of things. And they basically cycle up and down by pumping oil from the internal reservoir to the external reservoir if they want to rise, because that increases their volume, but their mass stays the same, so their density is lower. And by allowing that oil to go back into the internal reservoir if they want to sink. So pretty cool. I love this technology. Actually. Here's how many we have had out there as of this spring. There were about 200 floats in regional pilot arrays. About 50 of these are PMELs, a bunch are Scripps. We also have international collaborators in the UK, Australia, Japan, Europe, France. A whole number of countries are putting out these floats. We're going to look at Antarctic bottom water warming in a few of these regions. So the South Pacific, the Bellinghausen Basin here. We're going to go back to the Argentine Basin first. We'll look at the Brazil Basin. So these are all places where we have arrays, and we can see using the deep Argo data, if we can detect anything more than what we were able to with the repeat hydrographic data. Right. So this is actually the location of that repeat hydrographic section from the Argentine Basin that I was saying was gave us 1.9 plus or minus 2.2 milledegrees C a year warming below about 4,000 decibels. It's off to the side. But we actually have a whole bunch more data. So what I did was I took deep Argo data. This is just from about a year and a half of deployments, and those are the pluses. And I took all the historical shipboard data that was available from 1972 to 1998. So that's through the World Ocean Circulation Experiment. Those are the axes. And I compared nearby historical data, the orange axes, to nearby Argo profiles, which are the magenta pluses. And I just said, if they're within 165 kilometers of each other, I'm going to compute a trend. Right? So a whole bunch of trends, and then we can look at the statistics of those and average them in a basin-wide sense. When you do that, this is what you get. So we're looking at the trend versus depth from 2,000 meters down to the bottom. And this is the 5 to 95% confidence in intervals. And I basically said that any trend that has a time difference that's, well, basically in a 165 kilometer by 165 kilometer by 60-day bid. And I use 60 days because that's an eddy time scale. I use 165 kilometers because that's a dominant eddy time scale. Is statistically is independent. So you get a warming trend that's very similar to the warming trend that we got using the repeat hydrographic section, about 2 milladegrees C a year. But the uncertainties are much, much lower. They are a factor of 10 lower. Now we're using a lot more data. Part of that is because we can use a lot of historical data. Part of it is because these Argo floats zip around this particular basin like crazy. It's very energetic. But the end result is that we're getting, we're getting instead of a 2 plus or minus 2 value, we're getting 2 plus or minus 0.2. So we've increased the certainties tenfold. The other thing is if you think about, I talked about this reduction in Antarctic bottom water formation. A typical definition of pure Antarctic bottom water is it's colder than 0 degrees C. It's equivalent to a deepening of the 0 degree sea isotherm by about 200 decibars over this time scale, 34.5 years, for the time of the temperature trend that we're computing. So big change in depth of the isotherm, big reduction in Antarctic bottom water. You can do a little better than just looking at the basin-wide trend, though. And so this is where sort of improvements come in. We can see if we plot the trend versus latitude. The overall trend, this is at 5,300 decibars. So this is just one pressure level, a very deep one, that's down in the Antarctic bottom water. The trend is 2 milladegrees on average. I just showed you that in the last plot. But there is some spatial variability. You can see as you get down towards 49 south here, the trend tends to be a little higher, actually quite a bit higher, at the southern edge of the Argentine basin. And this pattern actually holds for 3 decades. If the Argo floats are all from, what I say, 2021 to 2022. But if we look at the 1970s, which are the red plus, the blue pluses, the X's, black X's from the 1980s or the 1990s, we see this higher values near the southern boundary persistent across all those decades. So this is kind of an interesting, it's not, we're already getting beyond basin averages here, right? And learning some new stuff. So if you look at the warming pattern and you look at the deep Argo temperatures, they are at minus 0.01 in the interior of the basin, and a little colder, minus 0.015, and maybe minus 0.007 near about 50 south at the southern part of the basin. If you look at all the historical data together, there's going to be some scatter to it because it is warming over time. But if you look at all of it together, you can see that the Hiccup temperature is 0.35. So it's warming much faster here, and that's because it's the coldest, densest water that are entering the basin, the ones that are closest to the source that are warming the fastest. Right? So that's consistent with what we might expect. You've got this cold, dense water entering. And it's warming the fastest, and then as it mixes into the interior, that warming is diluted a little bit. And if we look at another section now, we're going to look at the A23 section from the World Ocean Circulation Experiment, just to sort of show you in plan view what that looks like. And I've unfortunately got to cut the depth off on this section. I apologize for that. But this is probably about 6 kilometers depth at the bottom. And you can see, and it's going from 50 south, the left side of the 30 south, right? So I would say that near 50 south, this cold, dense water here is warming, right? And this is actually a signal of the deep western boundary current entering this basin. It enters from the southeast. Third portion of the basin flows west along this the topography at the south, this ridge at the south at about 50 south, and then north along the boundary. And so this deep shear, the coldest water, is actually warming up much faster, and it's this temperature gradient that actually supports that northward bottom intensified northward flow, right? So the bottom intensified northward flow is actually weakening over time, consistent with a shutdown of Antarctic bottom water circulation. You can assess the amplitude of that, and if you estimate the transport below 4,500 decibar, assuming zero velocity there, it drops from 10 spherographs to about 9 spherographs. And that is roughly consistent with a 200 decibar isotherm drop over 3.5 years that I talked about earlier. So we actually have less water coming into the basin. The amount of Antarctic bottom water is shrinking as a result. So the overall spatial pattern is actually consistent with what we're seeing from the trend at the basin. All right, stepping on to the Brazil Basin, we see a similar result. The Brazil Basin flows don't move around as much. It's quieter up there. So these are, again, the X's are repeat hydrographic sections from the 1990s. The pluses in magenta and blue are deep Argo float data. And we're just comparing the magenta with the yellow here. So magenta floats with the yellow or the orange hydrographic data. And again, we see about a 2 millidegree C trend. And its uncertainties are actually a little bit bigger than the ones in the Argentine Basin, even though we have more float data here. And that's because the floats don't move around as much. So we don't get as many independent estimates, right? They're not all spatially independent. But we still have a much better estimate of the warming rates than we did with repeat hydrographic sections. On time. Not bad. All right, now we're going to move to the Southwest Pacific Basin, and we can do a couple of different calculations here. There are a lot of floats. This was actually the first place where cargo floats were deployed. They were deployed back, the first two were deployed in 2014 by Scripps. They deployed the first real part of the array around 2016 and have been deploying floats ever since. So if we compare those deep Argo data, historical CTD data, this is just the deep Argo data. You can see a very clear warming signal again in the abyssal warming, in the abyssal waters below 4 kilometers, a little bit above 1 millidegree C a year. And in fact, you can look at the trends for the float data alone. So that's what the right-hand side figure is. I've been showing you long-term trends, right? Just decadal average trends up until now. This is actually a trend from 2014 to 2023. So it has a little bit bigger uncertainty than the long-term trend. But in the bottom water, the trend is also bigger, right? It's reaching up at around 3. So again, are we seeing maybe a little bit of acceleration here, right? That's the first time I've talked about that for the bottom water. But here it is. we are perhaps seeing that. In our little tour, I'm going to skip around to another ocean basin. I'm going to look now at the Bellinghausen Basin. So this is some work that I did with remotely with a summer student fellow at Woods Hole and Allison McDonald, here Mahmoud Sadman. So we looked at trends. We had section data here, and we said, well, we have data from the 1990s. We have data from 2005 to 2011. And we have data from 2017 to 2018, and then we have the float data, which was 2023 and 24. Right, so that they're color coded on this map from blue to orange to red to black here. And if we again look at nearby float data compared to historic data from those three different epochs, from the 90s, mid 2000s, and the late 2010s, what do we see in terms of trends? So here, the trend is close to 3 milligrees C per year in the 90s. That's bigger than we've seen in the Argentine or the Brazil or the Southwest Pacific Basin. That makes sense. This is closer to the Antarctic bottom water source. If you remember that original plot of the long-term trends from Sarah's work I showed you, it's larger near the sources. It gets closer to 4 milligrees C as you look from 2005 to 2023. And then if you look at 2017 to 2018 to 2003, it's up at about 8 milligrees C a year. So again, like the Southwest Pacific Basin, we're starting to see some evidence for acceleration of this warming. This is substantial warming. And actually, if you look at the last one, that's half the 2000 to 2023 global average SST warming rate of 17 milligrees C a year. Right. So this is really actually a pretty big signal, and it's not it's over a couple kilometers, and that's why when you globally average it, it can amount to about 8% of the global signal. Right. It's in places it's quite large, and it's persistent globally. All right. So this is like hot off the presses. Haven't even submitted it yet. But I'm going to talk about it anyways. So this is, Sarah and I talked about, well, why don't we try to combine the repeat hydrographic section data, but not just the repeats, but all the historical CTD data that we have with the deep Argo data, and try to estimate some trends globally. And so these are the results. This one on the left is for the abyssal layer. That's 4,000 to 6,000 kilometers. Again, these are temperature trends, maxing out at plus or minus 5 milligrees C a year. So, negative being blue, positive being red. And this is a deep layer, the average trends in the deep layer from 2,000 to 4,000 decibars. So what I've done is I've made all available historical ship-based CTD data, the deep Argo data. At 2,100 decibars, that's 66,000 historical data and 30,000 deep. I'm using it from everything that's available and flagged as good from 1970 to May 2024. I decided to bin these in 167 by 167 kilometer bins. No matter how many data I had in that bin, and just compute a trend. So long as the first point and the last point were separated by more than 10 years. Okay. And we're doing that at 10 decibar intervals from the surface to 6,000 decibars. So good pressure basis. That results in using about 70,731 profiles in 3,338 bins spatially, after discarding some extreme outliers. There is junk in the World Ocean Database. I mean, honest to God, junk, and you have to actually do a little free. But and again, that's at 2,100 decibars, and all these counts that I'm talking about are in decline as you go deeper. There's fewer and fewer data deeper. But the ocean area also shrinks as you go deeper. And so you'll see in a minute that it averages out to about 25% of the ocean area. So I then had trend estimates that are colored in all the little squares, inside all those little squares that are on there. So the left-hand side is any square that had a value somewhere between 2,000 and 4,000 decibars is included. Sorry, left-hand side is 4,000, 6,000 decibars, right-hand side is 2,000, 4,000. And then I use just a MATLAB natural neighbor interpolation to map data from where I had the samples to unsampled areas so that I could do a global integral. And that's basically a local weighted average. So it's just a way to smooth. It takes the nearest neighbors within some Moroni hull and averages them by area. So it's a little bit complicated to explain, but it's basically a weighted average. Okay. So we can then integrate these rates globally for deep 4,000 decibars abyssal layers, and I'll do that in a little bit. And I'll actually spend a little more time on these plots too. So let's move on. Just so you can see, this is again at 2,100 decibars. On the left-hand side is just, sorry about the log plot. This is the best way I could think of doing it. Most of the values, this is profile count. So in those 3,000 bins, you might have as few as 2 profiles. 120 of the bins, of those 3,000 bins, only have 2 profiles. They're separated by 10 years apart, but I've computed a trend. The mode here is 6 profiles within a bin. There's about 230 of those at 2,100 decibars. And then there are some bins that have hundreds and hundreds. Right? There's actually one bin off Hawaii at the Hawaiian Ocean Time Series that has over 500 profiles. So that's a combination of the Hawaiian Ocean Time Series, and we put 2 deep Argo floats there. Right? So we have a whole bunch of profiles. But on average, I should know how many there are on average. Like, you can see the distribution. And then on the right, this is basically all the bins looking at what the year of the first profile is in blue and the year of the last profile is in red. All right, so you can see sometimes I was actually computing a trend from 1970 to like 1980, right? A few of these, or from but for the most part, I'm on average computing a trend from about 2015 or 16 to I think 1987. The average here is 1987, right? So this is a long-term sort of trend. So of those, with those 167 by 167 kilometer bends that are sort of, on the eddy scale, what percentage of the ocean volume am I sampling? You can look at that versus pressure. And it starts up at about 30% at 2,000 decibars, gets to about 29% at 2,100 decibars, and decreases a little bit towards the bottom. On average, if you look at what the volume averaged sampling rate below 2,000 decibars is, it's about 27% of the ocean, right? And if you look on the right-hand side here, you can see the North Atlantic, quite well sampled. Sampled, almost everywhere in the northern Atlantic, up in the Greenland ice, Norwegian seas. And that's because historically this is just super well sampled by ships. Right? Same for the North Pacific, around Japan, US. Here in the deep ocean is pretty well sampled by research vessels. You can actually see people took PTDs on the Tau stations back through the 1990s. You can see those. That's a PML work there. And then in the South Atlantic, it's actually pretty well sampled too. That's a combination of good historical sampling by ships combined with the deep Argo array, right? Southwest Pacific, even though there's a lot of deep Argo data, the array is not 10 decades old yet, or a decade old yet, so I don't have a lot of Argo only, deep Argo only, because I need to have nearby shipboard data to make an estimate. And so there, it's only a slight, it's not as well sampled, even though there's a lot of deep Argo. Another decade ago, or another 5 or 6 years, I'll have a decade's worth of debargo data. You can start to calculate decade. We could probably try to find your trends now, actually. We just haven't done it. Anyway, so then, as I said, North Atlantic and North Pacific are pretty well sampled. Southwest Atlantic is also good. Southwest Pacific still not sampled. Everywhere else is still a little undersampled, right? But that's why we want a global debargo array. Let's just take a look a little bit more, in a little more detail at the deforming rates. I know those other figures were small, so this one's a little bigger. So this again is from 2,000 to 4,000 decibars. And there's a few patterns that leak out at me. One is that south of about 50, that's 50 south, the Southern Ocean is warming in that layer, right? There's a little bit of high amplitude noise just to the north of that. That's because the Antarctic circumpolar current, which has a big contrast in temperature between the warm waters to the north and the south water, cool waters to the south, is meandering around there. And so, you know, we might be aliasing some of that. That's a noise source to us, right? North of that, you see kind of blobbiness in the Pacific and the Atlantic, or at least in the Indian, or at least I do. These are very old waters. It's between 2 and 4 kilometers. The water in the North Pacific and North Indian, it's been for millennia since they last saw the ocean. So we don't necessarily expect a big warming trend or cooling trend there. And then if you go up into the North Atlantic, you can see a lot of warming up in the Jin Seas, north of and east of Greenland. That's because the deep convection there is actually shut down. And that those waters are warming as actually warmer waters in the Arctic flow back into that place, the waters that used to be cooled by deep convection. Similarly, it looks like in the Labrador Sea, we've had a lot of warming since like the late 90s to the 2000s. And you can see that up in the western subpolar North Atlantic. There's some cooling in the rest of the subtropical western North Atlantic and the eastern subpolar. I'm not sure what that is. It's probably again related to decadal variability in North Atlantic deep water formation. But that probably could use some more work to find out. If you look at the abyssal warming rates, you can see again warming that's sometimes up to 5 degrees C a year. In the Southern Ocean here, all the basins adjacent to Antarctica. And you can see this cool pattern of that warming spreading up into the Pacific, diminishing as it goes. Most of the Antarctic bottom water flows along the western boundary here, off east of New Zealand and the Tonga-Kermadec Ridge. That part is warming the most, right? And the interior part of that basin is not warming as much. Again, that's consistent with the coldest, densest waters actually warming, and that reduces that's consistent with a reduction in northward flow of the Antarctic bottom water into that basin, just like I talked about in the Argentine basin in some detail. You can see warming extending into the eastern Indian Oceans, Tasman Basin, the Peru-Chile Basin, the Bawa Basin, eastern Pacific. You can see warming extending into the western Atlantic, Argentine Basin, the Brazil Basin, and actually even into the North Atlantic along the western flank of the Mid-Atlantic Ridge there. The only places where you really see cooling are in the rest of the North Atlantic and in the Angola Basin in the eastern part of the South Atlantic. Those are actually basins that are not primarily fed by Antarctic bottom water formation. So the bottom water there is actually North Atlantic origin, so it's North Atlantic deep water. So we have a pretty consistent pattern of warming anywhere that there's Antarctic bottom water. And I said I would talk a little bit more about, let's look at the global averages first. So this is just, I'm just plotting a temperature trend. Remember I said the bottom water was warming sort of, the deep water was warming south of 50 south. So I just plotted these averages north and south of 50 degrees south. Right? So the blue line are the warming rates south of 50 degrees south. They average about 2 milligrees C a year. In the bottom water from 4,000 meters to the bottom, and then they're a little less in the deep water. The rest of the global ocean, north of 50 south, you see a warming of maybe half a millidegree C a year in the bottom water on average. Some places are higher than that, some places are lower, but the average is about half a millidegree. And then you see less warming, especially between about 3,100 and 3,500 decibars. That's the really old waters in the Pacific and Indian Oceans that are not warming at present. And then you can see this trend start to increase, and that's going to meet pretty well with the trend from Argo, the long-term trend from Argo that I showed you at the beginning of the talk was still not zero, was above zero at 2,000 decibars. So we sort of met that. So it's interesting. We proposed, Sarah and I, back in the early 2010s, that this Antarctic bottom water formation, that this warming was probably due to a reduction in the Antarctic bottom water formation rate. And there were already papers out that were proposing that there was freshening on the shelves of the Antarctica. So basically, bottom water is formed around Antarctica as very cold winds from the continent blow across polynyas, holes in the ice that extracts heat. As ice forms, that makes the water saltier. So making the water colder and saltier, both of those things make the water denser. That dense water spills off the shelves into the abyss and then spreads north in all the basins that we've been looking at, right? Everything but the North Atlantic and eastern South Atlantic. If you melt marine terminating ice sheets and inject fresh water above the shelves, that tends to inhibit that very dense formation and less bottom water forms. And this is a figure on the left from Fogwell et al. 2015, where they did a numerical modeling experiment where they enhanced meltwater flux around Antarctica. And so the black lines are control runs, and the colored lines here are various enhanced freshwater melt. They put freshwater to the surface, and you can see that, and then this is a rate of Antarctic bottom water formation, so about 7 million cubic meters a second on average in the control runs. As soon as you introduce that meltwater, bang, the Antarctic bottom water formation is drastically reduced, right? And so that's consistent with what we're seeing. If you look at temperature changes on the top panel, you can see this warming around Antarctica, south of about 50, 60 south, and then in the bottom water, more subtly and smaller, but still there, extending north. And so this is just a map from another more recent paper by Lee et al. That looked at a similar problem where they had wind. They looked at both wind changes, thermal warming, and meltwater. And the meltwater is really the dominant factor here. Is what this heat content on the accumulation map is. But I just wanted to show you the pattern that they show here for warming in the abyss from 1991 to 2023 and 2030. You can see some reminiscence, some resemblance to that Antarctic bottom water warming observed plot that I showed you. So the abyssal warming rates are actually expected to accelerate from model results in the coming decade. So deep warming is important for sea level rise, there's energy imbalance, carbon uptake, global ocean circulation, et cetera. So I'm just going to make a pitch that we should be monitoring. So this is Deep Argo in January 2024, color coded by nations. You can see there are 11 nations contributing floats. There are about 200, but we're really far from a global array. What One Argo is proposing, this is just the profile locations. So these are all the Deep Argo floats that as of January. This is our target, 1,228 floats global. So we're at sort of about 15% of the target. But if we do this, we can monitor what is clearly a changing deep and abyssal ocean. So conclusions. Ocean warming is 90% of global warming. Right? Ocean warming really is the global warming signal. Sorry, I did this slide like a few minutes before the talk. Sorry about the typo. Argo has allowed us to better quantify the warming, that warming, and its acceleration. Oh God. That is awful. Sorry, I never do that. Never. But yeah. Autocorrect. Deep hydrographic sections have detected global abyssal warming. Deep Argo regional pilot arrays, and I've showed you results from 3 of those, have improved our regional abyssal warming estimates, sometimes as much as tenfold, and in a couple places detected acceleration of that warming. Okay. And finally, I showed you global analysis of chip-based and Deep Argo CTV data. That actually improved the spatial resolution. Before we were just doing base and averages. Now we're doing maps and reduced uncertainties by about half. They've gone to from plus or minus 50% to about plus or minus 25%. We got, by the way, the exact same answer that Sarah got back in 2010. But like I said, we know better what the patterns are, and we know, instead of 50% uncertainty, we're down to 25% already. So this warming is caused by melting of Antarctic ice sheets and is expected to accelerate in coming decades. Global implementation of Deep Argo will allow us to better understand and quantify this phenomenon. Thank you. All right, put everyone to sleep. I see a few hands. John, I think your hand was up first.
Yeah, I'm curious if you could do the same thing with salinity data to kind of add to ECIs, or is it like would it have the same?
So there is a freshening signal that I didn't talk about today. I took 55 minutes already, right? But there is a freshening signal that is associated with that warming, especially close to the source around Antarctica. People have done that with repeat hydrographic section data. We did actually look at that using the Argo data in the Bellinghausen Basin recently. And we think we can see that freshening as well with the Argo data. It's not easy because the freshening signal is pretty small, but we think we can do it. I think Shidong has his hand up next.
Yeah, I think I missed a lot. So, the warming is caused by melting. I understand that melting slow down the sinking motion. But on the other hand, I'm thinking if the abyssal warmings connect to global warming, then the warming should start at the surface, right? And so my thinking is water getting larger, the surface water is thinking about just completely opposite from what you think. I don't know where I'm going.
So think about it's actually complicated, a little bit complicated to explain. But basically, if you think about the abyssal temperature budget in a steady state, it's a balance between inflow of cold abyssal water that's formed around Antarctica and mixing of heat from above as that water upwells, right? And so that's what, it's that combination of mixing from above and cold water coming in, being constantly renewed from below. And that's been going on for thousands of years, right? If you slow down the flow, it's going to warm down there, basically. So just think of it like a pipe model. The other way to think, and people also ask, how does the signal get all the way up into the North Pacific, right? So quickly, right? The advective timescales are hundreds of years. Well, the answer is that it's not, it's near the source, it's partly an advective signal, but everywhere it's also a heave signal. It's communicated by planetary waves, which have a much faster speed than the advective timescale. So basically, you reduce the amount of Antarctic bottom water coming in the basin. You set up a Kelvin wave that propagates along the west coast, gets the equator, propagates east as a Kelvin wave, goes poleward as Rossby waves and radiates into the interior. That takes about 40 years. That signal takes about 40 years to get up to the North Pacific, and the freshening has actually been happening in Antarctica since the 1960s. So it's all fairly consistent. If you don't like thinking about Rossby and Kelvin waves, I also think about it in terms of a balloon analogy, where imagine you have a balloon that has tiny holes in it. Those holes are the mixing, right? You're blowing into the balloon at a constant rate. The balloon gets big enough, and basically the air that's going out of those tiny little holes is equivalent to the air that you're putting into the balloon, right? It takes a while for that air from your lungs to get to the edge of the balloon and escape. But if you slow down the blowing, the wall of the balloon shrinks instantly. What's bringing that? Pressure waves, right? It's pressure waves in this case. They travel at the speed of sound. But those are what communicates the signal of that change in the inflow to the wall of the balloon, right? It's similar to the Kelvin waves communicating the signal forward. That was way more than you asked for, but I like to sort of try to tell that story.
All right, how about one more?
Yeah, there's anyone online?
No
No,
questions
that-
online yet?
I'm curious, what would it take to get your 1,300 deep Argo floods? Like what is the number?
Budgetary?
Like a budgetary number? Like what would it look like?
Yeah,
Like,
so-
how would you pull it off?
So it's basically, Argo right now is about $12 million a year that the US puts in. We want to actually go deep. We want to expand into the poles, and we want to do biogeochemical. So I'm going to give you a number for all of that. The deep probably doubles the cost. Biogeochemical more than doubles it. The end number is about 50 million a year from the US. That gets you full depth coverage, temperature, salinity, and 5 or 6 biogeochemical variables. 1,000 of those floats, 1,200 floats going through. Fewer core floats, because you add a lot of heat than BGC. But yeah, the overall price increase is roughly tripling or quadrupling.
All right, let's think, Greg, again.
Okay.